Hi, I am Kyle. I am presenting investigating the role of attribute, context, and vision language models for object detection and recognition. Building motivation for this work, we consider the typical use case of object detection and recognition. A standard way to achieve high performance is to fine-tune a model that has already been pre-trained on a large corpus of annotated data. Large-scale annotation is expensive, however, so more recently computer vision has been propelled by vision language pre-training between image-caption pairs. Focus is usually on the object nouns in the captions, though the signal is observably rich with attribute context as well. We aim to evaluate the utility of this context in object learning and various fine-grained tasks. Going over our research questions, we first ask what the existing role of attribute context is in object recognition and detection. Does attribute context play an impactful role in pre-training for detection? Does learning to ground objects to contextualize word embeddings effectively use attribute meaning? And do VL models perform well when the tasks have objects described with or in terms of attributes? Our second overall question is how can the utility of attribute context in object recognition and detection be enhanced? For this purpose, we investigate contrastive negative sampling, asking whether it can increase a model's ability to use attribute context, and we investigate what sampling mechanisms are most effective. Overall, to preview our contributions, we present a way to measure attribute sensitivity and alignment, and we propose an adjective-based negative sampling strategy that effectively enhances the influence of attribute context. Diving into our experimental study, we consider models that learn image-text alignment from image-caption pairs. This is done in a contrastive manner. Formally, assume a batch of images and a batch of captions which have corresponding pairs. Two objectives are optimized: an image-to-text loss that encourages the correct caption to be aligned to an image, and a text-to-image loss that encourages the correct image to be aligned to a caption. These losses in particular optimize the matching score IC. We analyze two specific frameworks that fall under this general categorization. First is region word grounding, which is a fine-grained alignment suitable for detection. We investigate the OVR-CNN framework, which is open vocabulary and faster RCNN based. Here, the alignment score is computed as a weighted average of dot product similarities between region and word embeddings. Secondly, we explore global image text alignment, which is coarse grain alignment suitable for recognition. We analyze the popular CLIP model, which has demonstrated impressive zero-shot classification performance. Here, the alignment score uses overall embeddings for the entire image and an entire text description. Now I will illustrate how we measure attribute sensitivity within these frameworks. First, for OVR-CNN region word alignment, we use unsupervised word grounding. Given an image caption, the goal is to return a bounding box matching an object word. Second, for CLIP image text alignment is the recently proposed classification via description task. This task is zero-shot classification using class names with large language model context. The key for measurement in both tasks is that attribute information can influence model decisions. Within these tasks, we measure performance under various text changes to gauge attribute sensitivity. We consider a baseline scenario using the original caption and description. We consider what happens when the attribute context is removed, positing that losing helpful info may hurt performance. We change the attributes as well, using plausible attributes based on ones mentioned with an object in a text corpus, along with random adjectives from a dataset. We posit performance should drop in an attribute-sensitive model when changing the attributes, as text can be made incorrect. Lastly, we stress test attribute understanding by removing class names. As humans can often know an object's identity given a visual description, we aim to see if describing an object by its attributes alone is possible. We also propose to enhance the role of context. First, for region word alignment, we observe that OVR-CNN leverages context-free embeddings, which may inhibit the use of attribute information. For example, the word orange would have the same embedding in these two captions. We propose to contextualize the grounding objective as a first step to enhance use of attributes. We find that this contextualization is non-trivial and therefore explore a training recipe in order to enable effective use of context. The recipe includes making sure the language encoder and vision to language projection layer are adequately updated, as well as using prompts and detection. Second, for both alignment mechanisms, we propose contrastive negative sampling of adjective-perturbed captions. We add a batch of negative captions to the image-to-text alignment loss, and then for these negatives, we make new captions, keeping all words the same but replacing the adjectives modifying object words. We explore two cases similar to our grounding setup, choosing a dataset plausible adjective as well as choosing a random adjective. So for green banana, possible negatives include rotten banana and pink banana. And then for region word grounding, to avoid a shortcut of just optimizing alignment of image to adjective word, we also explore random noun negatives. Moving to evaluation, we consider three downstream tasks. First, we consider open vocabulary detection, where due to the grounding learned, classes can be predicted even without bounding boxes in the training set. In this task, there are base, target, and generalized scenarios for which we evaluate. Secondly, we consider object attribution, which is choosing the caption with the right word order for a given image. We use ARO, visual genome attribution, and it's notable that cases are often nonsensical with this task. For example, paved house. We thus explore a third task to focus on plausible object attribute differentiation, which is text-to-region retrieval. We aim to retrieve regions matching a text query consisting of an object and then either color, pattern, or material, and we build off of the OVAD dataset for this task. So starting with gauging the role of attribute context, our first experiment is asking the question, what if we pre-train a vision language model without its attribute information? Does performance change? Interestingly, we find that the drops are not large from removing attributes. This is not what we would expect from a model that benefits well from attribute information. In fact, this points to wasted attribute context, and thus serves as its inspiration for enhancement. Next, as mentioned before, we explore contextualized grounding to integrate attribute context. We revisit our perturbation scenarios to see if models care about attribute meaning. When evaluating performance across these scenarios, we find that the differences are not very large, as shown in red. Both methods of changing attributes are close to baseline caption performance, which is counterintuitive since changing makes captions incorrect. Meaning is not well respected by default, bringing into question model fine-grained utility. We show here how adjective negatives address this challenge, as there are larger differences between baseline and changing in green. Overall, this shows that models may need an incentive to effectively consider object attribute differentiation. In our final gauging experiment, we look at CLIP and run the perturbation scenarios with classification via description. We explore multiple description and single sentence cases comparing to default CLIP prompting. Here, we find limited sensitivity in the multiple description case, but some more sensitivity in the single sentence case. A significant finding is that when class names are removed, performance substantially drops, as shown in red. Attribute-only descriptions are thus not sufficient for class differentiation. Now, evaluating our context enhancement and open vocabulary detection, here's a table with our strategies in the 5 open vocabulary settings. Regarding key insights, the top method overall in base and generalized is the one with all strategies, achieving up to +3 AP50 improvements. At a full scale, results improve state-of-the-art by at least 0.9 in 4 out of 5 settings. Overall, these results show benefits to better using attribute context. Notably, contextualized grounding is the driver for performance increases and enables adjective negatives to improve performance as well. Classes like oven, bear, horse, and frisbee are significantly aided by adjective negatives. These are classes often described with descriptive adjectives like colors, showing their aid in learning grounding. Finally, we observe a context-free contextualized trade-off when using our training recipe. We surmise that this comes from a need for a prompt with contextualized grounding, and without optimizing for target classes, the prompt may not be adequate. Future work can perhaps overcome this with better prompt design. Evaluating with retrieval and attribution. For CLIP, retrieval shown in the first 6 columns and attribution in the last column. We find that random adjective sampling helps the most in retrieval, and order perturbations, a competitive baseline we use, has the top performance on the order-based attribution task. Notably, random sampling has gains on both tasks, as shown in green, unlike the order baseline, which only helps on order. This shows more generalizable attribute understanding with the perturbed adjective captions. Random does better than plausible here, though with OVR-CNN we see competitive performance with random and plausible, and we see increases there as well. To conclude, we summarize answers to the research questions originally posed. Thank you very much for watching.